Hello, this is Shayan. Today I'm going to talk about a problem about shear flow in strength of materials. So this question is asking us to basically find the shear center and the shear distribution as well as the spacing of the nails of the basically vertical and horizontal nails that we have. And of course these as you can see, like, these are nails, but obviously of course they're not the best illustration, and nails, you can just stretch a little bit outward, of course, but these are just signify the connection, the nail connection. And where you do not see them, it's a glue-based connection, as you can see in the question. And of course we are assuming no slip between the two basically pieces that are connected. And of course, we have to know that they have 10 millimeter thick pieces, so all of these pieces are 10 millimeter. We have 13 of these pieces glued or nailed together. And of course, the forces of 100 kilonewton is applied either at at the left side or the right side to, of course, avoid twisting of the member. That's why you're finding shear center, which we're going to talk about later. Now, to start solving the question, the first step for us is to draw the shear flow diagram. Okay, the shear flow diagram is the most important step in solving this question. Now, the illustration of this question will help us the most. So let's go ahead and see what it looks like. So from the bottom, the shear flow starts, and from the flange, the shear is basically distributed and gathered to the neutral axis and then redistributed back to the flange from the bottom to top. And why is it from the bottom to top? Basically because we assume that our shear is applied in the direction of gravity. So the reaction or the flow, which is, again, you can consider kind of a reaction of the distribution of the shear, will be from the bottom to top. So as you can see, like, the web, which is the main shear carrying member, is basically resisting this shear applied either here or anywhere in this direction, of course, right? And again, let's take a look at it again. So we start from the bottom. From every flange, you can see that the shear is gathered, and we have the peak value in the neutral axis. Everything is gathered here and then gets redistributed to the other parts. Of course, we know that this cross-section is symmetric, as the question says, so everything's pretty much easy for us to draw and understand. Again, another time I'm going to run this so that you can understand how this flow is working. So as soon as this, basically the flange contributes to the web, basically you add the value, basically, right? This stress is added to this web, and web carries the value and then again redistributed. Okay, so this concept is very clear. Now, and this is very important to understand also from the perspective of flow, right? So we have flow in a lot of concepts in engineering, in any field, basically, and flow has basically the same concept. So a river, a flow, you can think about everything, right? Everything is gathered and then redistributed, right? So this is the very, very important first step that we have to start with. Now, next, we have to see what steps are going to follow. So I basically provided a procedure to solve shear flow problems. Now, in this case, what I will always do is to find the moment of inertia of the cross-section. And why do we do that? We're going to talk about it, but VQ over IT is our transverse shear stress, right? Now, V is known, right? It's 100 kilonewton for the whole cross-section. We're applying one load. T is known, right? T is 10 millimeter. Every piece is 10 millimeter thick. Now, the unknowns are Q and I. However, we do know that the cross-section has a constant. We have a prismatic cross-section, and which means that basically our moment of inertia is constant, right? Now, so basically what we can take away from this is that we can find this moment of inertia, and basically we have this V over IT as constant for this stress value, right? So V over IT is constant no matter which point we are looking at in this cross section. And the only thing that's going to change is Q. Now for the next step, that's exactly what we are doing. V, I, and T We know them now. And now the only thing we have to find is Q, right? And then we find the first critical points and calculate Q at those critical points. And we're going to talk about what those critical points are. Mainly, those are the connections. And again, based on the shear formula, calculate the shear stress. How? Of course, we know VIT, and now we calculate the Q. So we have everything to calculate this tau value. And it says draw the shear stress distribution for the flanges and web. And of course, when we have the shear stress, we can do everything else and find the corresponding force for each segment. And we're going to talk about these as well. This is about shear center because we have to find the corresponding force value to calculate the location of shear center to avoid additional twist. And for nail spacing, again, we are going to identify the shear planes and use the force equals stress times area formula to find the spacing between the nails. Now let's start with our first step. Our first step was to calculate the moment of inertia of the cross section, which is constant, as we know. I have done a very similar basically video which involves moment of inertia in the column capacity question. I will provide a link to that video in the description, and you can see that one as well. But again, we're following the same process, right? The process is to divide our basically pieces so that we can calculate our moment of inertia of the whole cross section. Now we do know the moment of inertia of an individual rectangular cross section. So what we do again is to say that, okay, maybe this piece and the bottom piece, we can take them as a group, right? And calculate the moment of inertia about the neutral axis. And again, because this cross section is symmetric, we do not need to calculate the moment, basically the centroid of this cross section because it's symmetric. So intuitively it's in the middle. And then another group, this piece and this piece, another one. All of these four will have the same moment of inertia about this global neutral axis. And we have this piece and this piece, these two pieces basically grouped together, and the last piece is the main basically web that we have. Okay. Now we have to basically group them together and calculate the moment of inertia of the whole cross section. And as we know, we have to just group them. 2I1, we have 2, 2, 4, 2, 2, and everything is clear from this cross section. Now, to calculate the first one, again, we'll say what is moment of inertia? Moment of inertia of, for example, this piece, only this piece, right? And because we have to, we multiply them by 2 at the end to account for both of them. But first we just calculate, for example, for one of them. So one of them, how is it going to look? The moment of inertia of this cross section itself, locally, about its own centroid, right? Which is going to be what? 200 times the height, basically its base, multiplied by height to the power of 3, divided by 12, which is what we have. 200 times 10 to the power of 3, divided by 12. Now this is local. Plus, we have to use the parallel axis theorem. What is the parallel axis theorem? It accounts for basically the eccentricity of this but basically the eccentricity of this segment from the global centroid, right? So here we will have 200 multiplied by 10, which is the area, multiplied by 400 squared, okay? And why is it 400 squared? So 200 times 10 is the area, we know that. What is the distance from the global centroid? It's from the center of this thin piece, right, to the neutral axis. And as you can see, by the way, these dimensions are all given center to center, so we don't have to worry about any of the thicknesses of any segment. So what is the distance? It's 100 plus 200 plus this 200 divided by 2, right? So it's 100 plus 200 plus 100, or 400 squared. We follow the same thing for I2. So what about I2? Again, it's the same moment of inertia of the segment locally, right? 200 times 10 to the power of 3 divided by 12, plus the area multiplied by distance. In this case, distance is just reduced by 100 millimeter. And basically, it's the same thing as I1. What about I3? For I3, we have, in this case, 10 is the base, right? 10 is the base times 200 to the power of 3, which is the height, divided by 12, which is what we have here. Plus the parallax theorem, which is the area, which is 200 times 10 multiplied by the distance squared. What is the distance? It's from the centroid of this segment to the global neutral axis, which is 100 plus another 100, so 200 squared. And for what about I4? So for this section, right, for this segment, we're going to have 200, which is the base, multiplied by the height to the power of 3, which is 10 to the power of 3 divided by 12, which is what we have, plus the parallax theorem, which basically says the area of this segment, which is 200 times 10, multiplied by the distance squared. What is the distance? 200 divided by 2, or 100. So 100 squared is what we have here. For 5, very, very similar process. The only difference is basically the area and the moment of inertia of this segment locally. Locally, we have 400 multiplied by 10 to the power of 3 divided by 12, which is what we have, plus the parallax theorem, the area, which is 400 times 10 with the thickness, multiplied by 100 squared, again, the distance from the global neutral axis. And finally, the main piece in the middle, which is the web, right? This piece 6, which is going to be 10, which is the base, multiplied by the height, which is 800, right? 800 to the power of 3 divided by 12, right? Again, the parallax theorem does not apply here because the centroid of this this segment is the same as in global neutral axis that we have, right? So our distance is basically practically 0. So the parallax theorem does not apply here. Now that we know all of this, we basically can use the formula that we have at the start, right? The I total, and just multiply 2 times this, 2 times this, 4 times this, 2 times that value, 2 times that value, and this value by itself. And we add those values together, and finally we get I total of 1.89 times 10 to the power of 9 millimeter to the power of 4. Now, we know all of the values that we should know except for Q. So we know V is equal to 100 kilonewton. The thickness of each piece is constant, right? 10 millimeter. If it's not, of course, we have to take into account separately, but in this case it is. So 10 millimeters is known, V is known, I is known, T is known. So the only thing that's unknown is Q. So our next step is basically going to be finding the Q value in critical points. So let's see how that goes. So this is our segment again. But the question is, how do we find the critical points? Mainly, the critical points will be in all of the connections. And what do we mean by critical points? And this is just a name just that I give, critical points, right? The important points that we are going to find. Now, why do we find them in the connections? We know that connections are usually the most critical points for us, right, in a cross section, because those are the points that you're trying to connect and avoid failure. Also, what we know is that as we go towards the web, so you move from here and you move towards the web, again, like from the flanges to the web, you are contributing to the shear effect in the web, right? So meaning that here, at this point, what is our shear value? The shear stress value here is 0. Why? Because there's no plane. There's no other plane. So we only have one plane, right? And this goes back to the definition of shear, right? Shear is created when 2 planes are in contact. Now at the edge, there is no shear plane, right? So there's only one shear plane. So from one shear plane, you cannot get a shear stress in this direction, right? So in the direction that we're looking at. Now, the shear stress here is 0. And for this flange, the maximum shear stress is going to be at this point, right? At this point where there's a connection. Same here for this flange. We have a maximum value here. For this flange, maximum value here. For this flange, maximum value here, right? So those basically signify our critical points. And that's our philosophy in finding the critical points. That's why we always want to find our critical points, to know basically what the maximum values are when we are drawing our shear stress distribution and for the flanges and the web, right? So let's start calculating the Q value. So first, before finding the Q, let's first find the critical points. So what are the critical points? It would be point A, which is the first connection we have it from the top. The other one will be point B, which is just to the right of the web in the second flange from the top. For C, which is just above the connection between the second flange from the top and the web, so just above this connection. And why do we do that? You'll see when we are drawing so all of this will become actually very clear when we are drawing the web shear stress distribution in the web and the flange, right? Especially in the web. So why we are finding the C, that's the importance, right? Because you have a Q value here and a contribution from this point. And again, I'm going to talk about the concept of moment of area, or Q. And here you have point D just below that connection, and you have point E right here at this flange, point F at this on this flange, and you have G, H, again above and below. You know, the main idea behind this is just find it at the connection, just to the left, just above, just below, and that's very important. Now, and again, the last one is the neutral axis, and we know that this condition is the maximum stress, maximum shear stress distribution at this point, right? And again, this has to also do with the fact that when our neutral axis basically means that our normal flexural stress is 0, right? And again, like our force is basically divided into shear and flexure in our assumption in elastic beam theory, and of course, when you have maximum shear, you will have 0 in moment and 0 in flexural stress, and when you have maximum flexural stress, you will have 0 shear, which is what you see like at the edges, right? Now, let's move to calculating the Q value. Okay. So the first point for us in calculating the Q value is to understand what moment of area, or Q, means. So we identified our critical points, right? And now we want to calculate Q in the critical points. But what is this moment of area? The name actually gives us a lot of information. The moment of the area, right? We usually calculate the moment of a force, which is again due to a mass or something like that. In this case, we are calculating the moment of an area, basically about the global axis, right? Now, how do we do that? What we can consider is all of the connections here, all of the connections here, this connection, all of the connections that you see as a hinge connection, right? As a hinge connection. And see basically the inclination or tendency of this member to fall. So what happens if this point A is a hinge? This piece is just going to fall, right? Just fall down. What about this point B? Again, the piece is going to fall down. Point E, fall off again, like to the left, right, we don't know. What about point F? You know, the same condition. What about point G? The whole thing here will fall off, right? What about point H? The whole thing here will fall off, right? What about point C? The top portion will fall off, right? What about point I? The top portion will fall off like this, right? So the concept behind the moment of an area is understandably really related to basically connecting the idea between mass and force to area, right? The same thing we're doing for force and mass, we're basically doing the same thing for area, right? So when we're calculating the moment of a force, that's the same concept, right? We are basically calculating the distance of this basically area. So what Q is the area, right? Which represents the force or the mass multiplied by the distance from the neutral axis. And we're going to see that. So how do we calculate the Q value? QA. How do we calculate this QA? So this is point A. Let's consider this a hinge, right? So this member is going to fall. So this piece is going to fall. And as you know, this A is just to the right of this web, right? Just to the connection between this flange and the web. So this piece will fall off and basically fall down, you know. So what would be the moment? The moment would be the area of this piece, which is 200 multiplied by 10, right? Which is the thickness, which is basically, in our case, you can consider this as our force, multiplied by the distance from the neutral axis, right? Which is what basically the arm of our moment, right? The distance from the centroid to the neutral axis is 100 plus 200 plus another 100, or 400. And that's it. That's our QA, right? The area multiplied by the distance from the neutral axis, right? And second, let's move to B. The same thing, right? For point B, we say, okay, let's consider this as a hinge. This point, this piece will fall off, right? This piece will fall off. Now, again, as we discussed, what is Q? The area or the force that we have, right? In this case, it is the area, right? Multiplied by the distance from the neutral axis. So it's 200 multiplied by 10, the area, multiplied by distance, which is 300, right? Again, the distance is from the centroid of this piece to the global neutral axis. For QC, we're going to have the same condition. So, however, we can be smart in calculating our Q values. And how can we do that? So, QC. So we'll say, okay, if this is point C, this portion will be falling off, right? So this will be, if this point C is hinge, this portion will fall off. Now, we'll say, okay, then we have to calculate the Q for this portion, right? This segment at the top, if we want to calculate QC. And another very important point, of course, before discussing this, is that you can also understand this based on saying that any point that you see, consider the area beyond those points, right? For point C, it would be from here, basically this portion, beyond that point. For point A, beyond that. For point B, beyond that. That's another way of looking at it. For point H, beyond this point, right? Not above, right? And above basically will work in some cross sections, but in this case, above, for example, if I say E, does it mean above like here? No, right? That analogy does not really work in these types of questions, right? So when we talk about E, for example, we're talking about this section. But now, yeah, so that was just another analogy that I wanted you to know, okay? So beyond, the beyond concept. Now, we're discussing this point C. Now, we said that if this is a hinge, this will fall off. Now, we can calculate the centroid of this segment and say that, okay, there's, the distance multiplied by the area that we know, we can calculate it. That's true. But the thing is, can we just say that this is a piece and this is a piece and just add them together? Because that's exactly the same concept, right, for centroid. So what we do is say QC is equal to QA plus the Q of this segment, right? Or you could say if these are two separate pieces, so the Q of this segment will be the QA, right? Or basically the Q of this segment, which is QA, right? Plus the Q of this segment, right? Because we know QC is the Q of this segment, right? The Q at point C is whatever area beyond this point C, right? That's falling off. So this will be this piece plus this piece. But we know this piece, right? This piece is QA, right? We calculated this before. So we can be smart and say that QA, which is what we know, plus the Q for this segment, which is going to be 100, multiplied by the thickness, 10, multiplied by distance. What is the distance? It's 100 plus 200 plus 50, right, for this segment. So 100 times 10, which is the area, multiplied by distance from the neutral axis. Again, distance from the centroid of that segment to the neutral axis. From that, you can get this value. Again, for point QD, for point D, for QD, we can again calculate everything once more, right? But the smart thing to do is say, okay, it's whatever above this, whatever we have above this point D. So we can basically say QD is equal to QB plus QC, right? Because it's all the segment. So we can say QC basically consists of this segment. QB consists of this segment, And that's all I'm looking for. So QD will be equal to QB plus QC. And of course, you can do the calculations by themselves, and you will see that the answers are exactly the same. So, while we can find all of these values, why not, just add them together when we know them, right, already. What about point I? Point I would be this QD, right? What is the segment? The segment will be this segment, right? This segment. But QD basically considers this segment, right? So the only segment that we have to consider for is this little rectangular segment, right? So say QD, which basically consists of this segment, plus the Q for this segment. What is the Q for this segment? It's just 10 times 200, which is the area, multiplied by distance. What is the distance? 100 plus 2 plus 100, right? 200 divided by 2. So 100 plus 100 will be 200, right? 200 times 10, which is the area, multiplied by the distance that we just saw. What about QE, right? This is the exact same concept. Whatever beyond this point. So 200 times 10, which is the area, multiplied by distance, which is 100 plus 100, which is 200, right? So area multiplied by distance again. QF, exact same thing, right? So left and right, so this exact same concept. What about QG? For QG, we'll say, okay, what area is going to be considered here? This area. Why? Because this area, if this is a hinge, this area is going to fall off, right? If this is a hinge, this area is going to fall off. Now, we'll say that, okay, again, or in other words, whatever beyond this point G that we have, right? Beyond this point G, which is this area. So what is the Q for this area? It's the Q for this area and the Q for this area. But the thing is, we know the QF already. This is QF. So we say QG is equal to QF plus the Q for this area. What is the Q for this area? Area, which is 200 times 10, multiplied by distance. What is the distance? It's 100, right? So area multiplied by distance. We end up with this value. What about QH? The same thing, right? So QH is equal to QE, right? Again, what is the area? Is this area, right? QH is this area. Right, so QH is equal to Q of this segment plus the Q of this segment. This segment, the Q, we know it, right? It's QE. Plus QE will be plus the Q for this segment, right? So it's QE plus the Q of that segment, which is 400 times 10, which is the area of the segment, multiplied by the distance, which is 100, okay? And we end up with this value. What about QJ, right? Which is just below the web connection, right? So just below the connection of the flanges we have. So it would be the area of the whole thing, right? Just above. So just above we have whatever we have here, right? Not the neutral axis. Point J is just below this connection. So basically this is the contribution. We can see that this segment at the top, and the segment on the left, right? But we know the Q of all of those segments, right? We can say QJ is equal to QG, which represents this segment, QH, which represents this segment, and QI, which represents this top segment. So QJ is equal to actually QH plus QI plus QG, right? You see? So you could calculate all of them separately, but we already know all of those values, right? We already know QG, I, and H, which represent these segments. So no need to further complicate this stuff for ourselves, okay? And we have the Q about the neutral axis, right? The Q about the neutral axis, which is the maximum value, right? So what about this neutral axis? Whatever we have above or below, right? So neutral axis is unique in this case, right? So we have neutral axis, whatever we have above here, right? So, or beyond here, right? So whatever above here is going to be QJ plus the Q for this segment, right? QJ, which represents this area, plus this area, Q for this area, which is not covered, right? And that's how we calculate basically this value. So QJ plus 100 times 10 times 50, why the area for this is 100 times 10, the thickness, multiplied by the distance from the neutral axis. The distance is from the centroid of this segment, which is going to be 50, right? From the centroid to this neutral axis, which is going to be 100 divided by 2 or 50. Okay, so that's how we calculated all of our Q values in the critical points, right, that we found. Now let's calculate the shear stress at the critical points, right? Now that we know our Q value, from the formula we can say tau is equal to VQ over IT. And we know we already knew basically V and I and T. And we also calculated the Q value at each of these points. So we can calculate the stress at basically any of these points that we know, right? But there's a very, very good step to add to this, right? What is that step? Is to say that, you know what, instead of just every time using a calculator and saying that, oh, okay, 100 times 10 to the power 3 multiplied by Q divided by I and T, we know that all of these for this question are the same. We have the same V, we have the same T, and we have the same I. So all of these are constant. So we say, you know what, just take this away, take this out, and say that this is K. K is equal to V over IT, and this value is a constant. So we say that, okay, so we can say that this value multiplied by the Q value for each of these segments that I found will give me my stress value at that point, right? What do we mean by that? So if you can see, we can basically write this, right? Tau is equal to K multiplied by Q. Why? Because K is equal to V over IT, right? We just assigned this V over IT to our K value. So tau is equal to K multiplied by Q, right? And this is the K value, which is constant, right? Which we have, as you can see, for all of the calculations, multiplied by the Q. And Q values were just the values we just calculated, right? In the previous page. Now, knowing all of those, just multiply all those values, and you will end up with the stress value at those points, right? The stress values at each of these critical points. Now, we now know all of our stress values in these critical points, right? Now we are basically ready to calculate our shear stress distribution for the flange and the web, right? Let's start with the flange first. For point A, we calculated our stress value, right? What was the value? It was 4.17, and we know that at the edge of this flange we have 0, right? Because there's no plane, there's no planing contact, so we have 0 stress here, and it increases linearly to point A, 4.17 megapascal. And one question you might have is, why is it linear? There's a proof that you can find in strength of materials books. I'm not gonna go over that concept, but it's good to know that the stress distribution in the flange is basically always linear, and for the web we have a parabolic distribution, right? Again, these are all based on the assumptions that we have for the shear stress formula, right? Tau is equal to VQ over IT. Now, that's for point A. For point B, we found 3.13 at this point B, right? So it increases from 0 to 3.13, right? What about point F? We have from 0 to 2.09, right? At all of these points, at all of these connections, as you can see, we found our stress value, right? So that's just what we're doing. Nothing really, difficult or worrisome about it, okay? What about point E? Exact same concept, right? So point E, we have the stress value that we just found based on Q, right? Again, what was the stress? It was that K value multiplied by the Q at this point, right? Which we calculated in the previous pages. And a very important part is for this segment, for this flange. You might think that it starts with 0. But the thing is, at this point, at this connection, we already had this 2.09, right? So there is a connection. It's not 0, right? Why? Because we already have a shear plane in contact, and the shear stress in this connection was 2.09, as we calculated before, right? At point F, we had 2.09. So we do not start with 0, right? Because we already have a shear stress value. So we say it starts with 2.09 and it goes to 3.13, which was the value we had here, right? That's very important to consider. So this does not start from 0. Why? Because this point F and like this point here, they're basically the same points, right? When we're considering in terms of shear value and the fact that these are thin pieces of basically 10 millimeter, right? And the same thing for point H, right? So for this segment, it starts from 2.09, which is what we had previously here, right? To 4.17, which is the tau H value that we just found. And the rest will be symmetric, right? So everything will be symmetric here for all of these other segments. Why? Because our cross-section was basically symmetric. So that's it for the flange. Now, what about the web? So for the web, it's very important to understand it because basically webs are the main shear carrying members of a cross-section. So for a web, we say, okay, let's start from our first point, right? Point A. So we start with this point, and we say, okay, already there is a contribution at this point, right? It's tau A, right? So this is the point in the web. So A either here or here, it really doesn't make any difference. So this is the same point here, right? So we have 4.17 just at the start. So we draw a vertical line, right? So just at the start, we have 4.17 megapascal of stress. And then as we move down, and as we mentioned, the stress distribution is parabolic in web, right? So if you move down, we'll see a parabolic distribution, as you can see, 6 megapascal. And where do we get this value? This is point C, right? We calculated tau C in the previous page. So tau C is 6 megapascal. And then we move and we see, okay, a flange is added, right? So we calculate this point D. So basically what we're doing is going through all of the points in the web. So point A, point C, point D, point I, point J, and the neutral axis. This is what we're doing basically. So it started with this point A. We had the contribution of the flange, 4.17. And then we moved to point C. What was the value? It was 6 megapascal. And then you move down to D. And here we'll have a jump. Why do we have a jump? Because this is a flange, right? So there's really no distance, right? This is just a jump, right? And another way to explain this is that basically this distance is considered zero in our calculation, right? So this point C is just above the connection. This point D is just below the connection. So there's no distance between C and D for this to be a parabolic or something like that, right? So it's just an addition to the web, right? An additional stress to the web, right? So suddenly you just add 3.13 megapascal to this 6 megapascal that we already had, right? Which is 9.13 megapascal. Again, 9.13 megapascal was the value that we found previously for each of these points, right? So the easy way is to just start with this point A, move to point C, D, I, and J, and know where you're basically going vertical or horizontal like this, and when you're going parabolic. When you have a flange addition, it's just suddenly you have an additional stress, right? Additional shear stress. So that's when you have a jump like that. So from point C to D, we have a flange. So there's a sudden increase in stress like this, right? And then you move to this point I. So for this point I, you can see that we have 11.22 megapascal. And as you can see, there is a distance, right? So this goes in a parabolic way of distribution. And then you move to, from point I, just below the connection, you have this point J, right? And because you have these flanges, as I mentioned, when you see flanges, there's a jump, right? Because there's a contribution from these flanges to the web. So there's a jump from 11.22 to 18.52. Again, all of these values is what we calculated in the previous page for each of these points, right? Point A, point C, point D, point I, and point J, and the neutral axis. And neutral axis, again, you see you have a distance here. So because you have a distance, you will say that we'll basically draw this as a parabolic distribution, right? And as we know, from the start to the end, basically from the start, at the start, our stress is 0, and then we move to the max, right? This is the peak stress in the neutral axis, right? The peak shear stress will occur in the neutral axis. And the rest will be symmetric, right? So 18.79 is the shear stress value we found for the neutral axis, and just basically just simulate the same distribution symmetrically to the bottom portion, right? Starting from neutral axis to this point, right? Which you could call A prime, right? So this is how we draw how we represent the shear stress distribution for flange and the web of a cross section. Now that we basically found the stress values for the flange and the web, we are ready to calculate and know what our forces are. So what are the forces? So first, this is why I drew this basically shear flow diagram at the start, right? So just on the first page, we basically discussed this point. Now, this was the shear flow diagram that we had. Now, for each of these segments, all of these segments will basically represent a force, right? So this, you could say that the stress value for this segment multiplied by the area of the segment will give us the force for the segment. How does this force look like? It looks like something like that, right? So we can represent these flows, right? Because what is flow? Flow is force, or shear force in this case, per unit length. So if we want to represent the area from the force, right? So we say force is equal to this stress that we have multiplied by this area, right? The same concept behind that, okay? And force F2, F3, F4, and F5, and F6, right? And all of these forces have one thing in common, right? First of all, of course, they are symmetric, right? So for example, I took this segment and this segment as F5, this segment as F4, this segment and this segment as F4, this segment and this segment as F6, and so on. And very important point is the direction, right? And that's why we draw the shear flow diagram. Because our shear flow diagram in this case is to the left, the force direction is going to be to the left as well for all of them, right? So for example, here your flow is to the left, this is to the left. Your flow is to the right, this is to the right. Flow is upward, this is upward. Upward, 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 you see? So all of this, so there's a reason behind drawing a shear flow diagram and see how our shear flow is distributed, how our shear force is distributed in the cross section across each segment, right? And see how all of these are basically translated into a force, and based on those, of course, we're going to find the shear center, right? That's the importance of knowing basically the shear flow diagram. Now, basically, we can calculate each of these forces, right, individually. How can we do that? We know that F, force, is equal to stress multiplied by area. However, for each of these segments, you can see that the stress is variable, right? So stress varies from 0 to the maximum, here 0 to maximum. Here, for example, it varies from 2.09 to 3.13, right? So the stress is not a constant value that, we can calculate, just multiply by A and find the force. So we can just use a tau average here, right? So what is tau average, for example, for this force F1? We could say this area, right? Multiplied by the tau average. What is the tau average? It's just 4.17 divided by 2, right? Or 4.17 plus 0 divided by 2. Why? Because this stress is basically linear, right? So it's a linear triangular distribution that we have. So just say 4.17 multiplied plus 0 divided by 2. That'll be our tau average. So 4.17 divided by 2 multiplied by the area. Same thing for F2, right? The 3.13 divided by 2 multiplied by this area, right? Again, stress multiplied by area gives us the force. And the value you'll get, of course, in this case will be millimeters squared multiplied by Newton per millimeter squared. You'll get Newton. Just divided by 1000, you will get 4.17 kilo Newton, okay? For F3 here, F3 is right here. And this is the segment that we're discussing here. Area of this segment, which is 200 times 10, multiplied by the tau average. What is tau average? Is 2.09 divided by 2, right? Or 2.09 plus 0 divided by 2, right? The average stress value. F4 and F3 basically have the same exact basically idea behind them, exact same value. F5, however, is different, right? So because F5 is not starting with 0, right? So for a representative stress value for this segment would not be 3.13 plus basically 2.09 divided by 2, or 2.09 plus 4.17 divided by 2, right? In this case, we were starting with F5, so this is F5, this is the segment. So it would be the stress of this point plus the stress of this point divided by 2, right? The idea behind this is just finding an average stress that represents the whole segment, right? That's all it is, right? That's why we say 2.09 plus 4.17 divided by 2, right? That's what we have here. From the previous one, what we did was just 4.17 plus 0, right? 4.17 plus 0 divided by 2. 3.13 plus 0 divided by 2, right? Same thing. In this case, we were doing 4.17 plus 2.09 because our first point here was not 0, right? Again, multiply by the area, we get the value. Again, the same concept here, 2.09 plus 3.13 divided by 2, multiplied by the area of this segment, which is 200 times 10. Now, those are the force values. Now that we know all of these forces, we can basically find the shear center, right? What is the idea behind shear center? Shear center is, we're finding shear center to avoid additional twist, right? So if I take the moment of this, basically across these forces, all of these forces, about this point, about any point, right? My segment should be in equilibrium, right? So that's basically the idea behind behind the statics behind all of these questions, right? So, however, if I basically apply this force anywhere I like, I'm not going to end up with the result that I want. So my segment will not be in equilibrium. In fact, I will end up with an additional twist in my section, right? So based on the assumptions that I made, I will basically have to recalculate everything, right? So because that's against my assumptions, right? Those are not the assumptions that we have in our shear formula. So what we do is find the shear center to avoid additional twisting. So we say, okay, you know what? If we say, okay, what is the concept behind shear center? We say, if I basically apply my shear force, right, in a specific point, then my additional twist will not exist, or I will not end up with the additional twist, right? Or additional torsional stress. And that's the idea behind it. So we say, okay, so there's a distance from this web to the, to the location I apply my shear force, where my twist will be 0. So that's what we're trying to find. So just take the moment about any point. In this case, we're going to take the moment about the web. And the reason is, about any point in the web basically. And the reason is that we did not find, if you remember, we found F1, F2, F3, F5, but there's also a force, a very large force in fact, in the web, right? There's a very large force upward in this web member. However, the calculation, an average calculation for that one would be very complicated, and it would in fact be very inaccurate, right? For flange, we know it's linear, but for the web, it was like parabolic. We had jumps in the shear, basically web, the shear stress distribution in the web. So it was very difficult to calculate an average value, and that would basically make our calculations very inaccurate. So what we do is just get rid of the force that we are required to find for the web, just by saying that let's take the moment about any point in the web. So what would be the moment resulting from this force? 0, right? Because the distance is 0. So this force would not create any moment. That's why we were basically calculating the moment about this point in specific, right? It's easier to take it about this point, or of course any point in the web, right? And another point that I can make, and I can talk about, is that your shear, in my experience at least, your shear center will be always, or usually at least, to the side of less material, right? So if this is your web, and you're going to decide if it's to the right or if it's to the left, it is usually 99% of the time to the left, right? Because you have less material here, right? And basically, consequently, basically lower forces, and and this is just by experience, right? So this is just a rule of thumb. But of course, for wherever you consider, it doesn't really make any difference. You can consider the force here, and just for your E value, you will see that this negative, it means that it was on the other side. That's all. So it doesn't make any difference at all. Okay, so it's just your initial assumption. Now let's take the moment about this point, this NA, right? Sigma M NA should be 0, right? Because our cross section is in equilibrium. Now, how do we calculate that? It's just basically a simple statics question, right? So you will just say F1 multiplied by this distance, right? And F1 multiplied by distance, right? Again, based on our convention, we considered our counterclockwise to be positive, but this F1 and this F1 are both clockwise about this NA, right? So they're moving in the clockwise direction both. So see F1 multiplied by 400, which is the distance, right? Which is basically 100 plus 200 plus 100, but multiplied by 2, right? Because I'm calculating two forces, right? This force, the moment of this force is F1 multiplied by 400, which is the distance, multiplied by 2, because I'm also considering this force. Same idea for F2, right? Moving clockwise, again, negative minus this force multiplied by the distance, right? And what is the distance? Is 200 plus 100, right? 300, see? And again, all of them multiplied by 2 because we have two forces, right? Or basically what I'm doing is just saying F2 multiplied by 300 plus F2 multiplied by 300, right? So that's basically the same thing. What about force F3? It's going to be this force, right? Multiplied by the distance. What is the distance? It's this distance, right? This distance is going to be 400, right? F3 multiplied by 400, of course, multiplied by 2 because we have another force, which is again turning counterclockwise for this segment, right? F4, F5, F6, all of them are the same thing again, right? So F4, we have this force multiplied by this distance. What is this distance? It's 200. So right, and again, like this is moving in the clockwise direction. So 2 times, basically F4 multiplied by 200 multiplied by 2, but of course negative because it's clockwise. And y is multiplied by 2 because we have another F4 here, right? So we have F4 here and F4 here. And of course, both of them are moving in the basically clockwise direction, right? So, and again, F5, we have this force. So again, as you see, this as well as this force are moving in the basically in the clockwise direction. Again, it's negative F5 times 100, right? F5 multiplied by 100, which is the distance from this point, right? Again, we're calculating all of the moments from the forces about this point, right? So again, force multiplied by distance, right? 2F5 multiplied by 100, right? So F5 multiplied by 100 multiplied by 2 because we have another force, right? Or basically F5 multiplied by 100 plus F5 multiplied by 100, okay? Same thing for F6, right? So F6 multiplied by 100, F6 multiplied by 100. Of course, this is in the counterclockwise direction, so it's positive. Now, plus the shear force that we applied, right? So 100 multiplied by E. And this is going to be actually in the counterclockwise direction, so it's positive. Plus 100 times E. So when we solve this, and as we know, we found F1, F2, F3, F4, F5, F6, all of them in the previous page, right? We find E and we find 58, and it's positive. This means that our assumption was correct. That basically this, the assumption that this is to the left, right? The force is to the left. If we found the E value to be negative, it means that this was not here. It was here. Basically, it was like 58 millimeters to the right side, right? So, but the force would be applied here, okay? And again, why do we find shear center again? It's just to avoid additional twist or torsional shear stress in the cross section, okay? Now, let's talk about the nail capacity question and the spacing of the nails. So as you can see, we have the cross section will look like something like this, right? So it will look like something like this. This is the connection. Again, these are the nails, right? So like these are the horizontal nails. These are the vertical nails. Now let's start with this horizontal nail first, right? The horizontal nail, which is here. So what is the plane that this nail is connecting? It's like this line in this case, right? It's this line. And you can see that this plane can be represented in this way, right? This is the plane. So this is the connecting plane right here, and these are the nails. And these nails will have a spacing. Now, what is the stress value that we have, this nail is carrying, right? And we can find it. So basically, what is this? This is the tributary area for this nail, right? So the tributary area for this nail. So basically, this nail is transferring the shear stress from the segment to this segment, right? So for this portion, right? And what is that portion? It's the spacing multiplied by the thickness, right? The spacing multiplied by the thickness. That's the area that this nail is covering. Again, we can visualize it from like what the tributary area for each nail is. Okay. Now, we can just move forward and say, okay, what is force? Is stress multiplied by area. And we already know that the capacity of our nail is 5 kilonewton. But what is the area? As we mentioned, what is the area? It's T multiplied by S, right? This area that the force is applied, right? Again, what the shear plane, this is basically our shear plane, okay? And the thickness is known as well, right? It's like 10 millimeters. Now, the stress at this point, so what is the stress that is being transferred? Is the stress at this point, right? But what was the stress at this point? We already calculated all of them, right? So we already know all of the stress values. So our stress basically is 4.17, right? From what we calculated before. And we could say basically, okay, if we know our area, so area is equal to ST, so F is equal to tau TS, right? Tau TS. So S will be F over tau T, right? So we know 5 kilonewton, which is 5,000 Newton, 4.17 megapascal, 10 millimeter as the thickness. We get this spacing, right? So we can just use 100 millimeter center to center spacing, right, in our cross section. Okay, so this is for the horizontal nails. Okay, now let's move to the vertical nails that we have. For the vertical nails, this is the basically nail problem that we're solving, right? So these are the basically the vertical nails, and this is basically the plane that we see connected, right? So what is this? If we magnify it, the tributary area for this nail is going to look something like that, right? For each nail, which basically means that the area is the spacing multiplied by T again. See, like the same concept. So we have again stress multiplied by area. The capacity of the nail is 5 kilonewton. The area is known again. It's tau T, and the T is known 10 millimeter. The stress at this point, which is basically what we found before, it was tau F, I think. Tau F, yeah, tau F and tau E. Again, tau E was here, tau F was here, and it's 2.09. So basically, again, the same formula. S is equal to F over tau T, and 500 Newton over 2.09 multiplied by 10 millimeter. Well, we can basically use 225 millimeter or 200 millimeter center to center for our nail spacing. And that's it for this question. So if you enjoyed the video, please like and comment down below, and subscribe for more content about problem solving in structural engineering, and see you next time.